When sizing a multiconductor flexible cable for ampacity, it's crucial to understand whether conductors used for control circuits are considered current-carrying conductors. According to the National Electrical Code, specifically Section 310.15 Con, the answer is yes. To illustrate this, consider an example involving a 12 American wire gauge, 6-conductor SOW cable. In this scenario, 3 conductors are used for power, 1 conductor serves as the equipment grounding conductor, and the remaining 2 conductors are connected to thermal switches within a motor, linking them to a 120 volts control circuit located in a motor control center, or MCC. The question then becomes how many conductors are classified as current carrying for ampacity calculation purposes. In this specific example, because the conductors connect thermal switches in a motor to a 120 volts control circuit in an MCC, they are indeed considered current-carrying conductors according to NEC 310.15 Con. Therefore, in the 6-conductor SOW cable described, there are a total of 5 current-carrying conductors. This is because the 3 power conductors and the 2 control circuit conductors all actively carry current during normal operation. It's important to note that the equipment grounding conductor does not carry current under normal operating conditions and is therefore not counted as a current-carrying conductor for ampacity adjustment or correction factor calculations. The significance of correctly identifying the number of current-carrying conductors lies in its direct impact on the allowable ampacity of the cable. The NEC provides tables and guidelines for determining the ampacity of conductors when multiple conductors are bundled together or are located in close proximity, as is the case with multiconductor cables. This determining is necessary to prevent overheating and potential insulation damage, which could lead to electrical hazards. Therefore, failing to include control circuit conductors in the count of current-carrying conductors would result in an inaccurate and potentially unsafe ampacity calculation. This, in turn, could lead to the selection of an undersized cable, increasing the risk of overheating, insulation failure, and ultimately, electrical fires. Let's delve deeper into the implications of NEC Section 310.15 Con and how it governs the ampacity adjustment of conductors in various scenarios. This section outlines the requirements for adjusting the ampacity of conductors based on the number of current-carrying conductors in a raceway, cable, or earth. The purpose of these adjustments is to account for the heat generated by multiple conductors carrying current in close proximity to one another. The heat generated by each conductor contributes to the overall temperature within the enclosure, and if the temperature exceeds the insulation rating of the conductors, it can lead to premature degradation and failure. The NEC provides adjustment factors in Table 310.15 Con which are used to reduce the allowable ampacity of conductors based on the number of current-carrying conductors. These factors are applied to the base ampacity rating of the conductor, as determined by its size and the insulation type, to arrive at the adjusted ampacity. For example, if a cable contains 7 to 9 current-carrying conductors, the ampacity of each conductor must be reduced to 70% of its base rating. Similarly, if a cable contains 10 to 20 current-carrying conductors, the ampacity must be reduced to 50% of its base rating. These adjustment factors are cumulative, meaning that if a cable is also subject to other determining factors, such as those related to ambient temperature, the ampacity must be reduced accordingly. In the context of control circuits, it's important to understand the types of loads that these circuits typically serve. Control circuits are commonly used to operate motor starters, relays, solenoids, and other control devices. These devices often draw a significant amount of current when they are energized, and this current must be taken into account when determining the ampacity of the control circuit conductors. Furthermore, control circuits may be subject to frequent switching, which can generate additional heat due to the inrush current associated with each switching event. This inrush current can be several times higher than the steady-state current drawn by the control device, and it can contribute significantly to the overall heating of the conductors. Therefore, it's essential to carefully consider the characteristics of the control circuit load when selecting the appropriate size and type of conductors. In addition to the number of current-carrying conductors, other factors can also affect the ampacity of conductors, such as the ambient temperature and the presence of other heat-generating equipment. The NEC requires that conductors be derated when they are installed in locations where the ambient temperature exceeds the insulation rating of the conductors. This derating is necessary to prevent the conductors from overheating and failing prematurely. The NEC also provides guidelines for derating conductors that are installed near other heat-generating equipment such as transformers or lighting fixtures. The heat radiated by these devices can raise the temperature of the conductors, reducing their ability to dissipate heat and potentially leading to overheating. To ensure the safe and reliable operation of electrical systems, it's crucial to follow all applicable requirements of the NEC when sizing conductors. This includes accurately identifying the number of current-carrying conductors, applying the appropriate ampacity adjustment factors, and considering other factors that can affect the ampacity of conductors, such as ambient temperature and the presence of other heat-generating equipment. By adhering to these requirements, electrical professionals can minimize the risk of electrical hazards and ensure that electrical systems are properly protected. Let's consider some additional examples to further illustrate the application of NEC Section 310.15 current in different scenarios. Imagine a scenario where a 10 American wire gauge 4-conductor tray cable is used to supply power to a series of lighting fixtures. In this cable, 2 conductors are used for the ungrounded, or hot, conductors, 1 conductor is used for the grounded, or neutral, conductor, and 1 conductor is used for the equipment grounding conductor. In this case, the 2 ungrounded conductors and the grounded conductor are all considered current-carrying conductors. The equipment grounding conductor is not considered a current-carrying conductor because it only carries current under fault conditions. Therefore, the ampacity of the 10 American wire gauge conductors must be adjusted according to the number of current-carrying conductors in the cable, which is 3. Now, let's consider a different scenario where 14 American wire gauge 5-conductor control cable is used to connect a programmable logic controller, or PLC, to a series of remote input/output, or I/O modules. In this cable, 2 conductors are used for the 24 volts direct current power supply to the I/O modules, and the remaining 3 conductors are used for signal communication between the PLC and the I/O modules. In this case, the 2 conductors used for the 24 volts direct current power supply are considered current-carrying conductors. The 3 conductors used for signal communication are also considered current-carrying conductors because they carry current during normal operation. Therefore, the ampacity of the 14 American wire gauge conductors must be adjusted according to the number of current-carrying conductors in the cable, which is 5. It's important to note that the NEC provides exceptions to the ampacity adjustment requirements in certain situations. For example, conductors that are used for short periods of time or that carry intermittent loads may not be subject to the same ampacity adjustment requirements as conductors that carry continuous loads. These exceptions are outlined in NEC Section 310.15 and should be carefully reviewed to determine whether they apply to a particular installation. In addition to the ampacity adjustment requirements, the NEC also specifies requirements for the overcurrent protection of conductors. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect conductors from excessive current that could cause overheating and insulation damage. The size of the overcurrent protection device must be carefully selected to ensure that it will trip before the conductor is overloaded. The NEC provides tables and guidelines for selecting the appropriate size of overcurrent protection devices based on the ampacity of the conductors. When sizing conductors and overcurrent protection devices for control circuits, it's important to consider the potential for short-circuit currents. Short-circuit currents can be significantly higher than the normal operating current of the circuit, and they can cause severe damage to conductors and equipment if they are not properly protected. The NEC requires that control circuits be protected against short-circuit currents by using overcurrent protection devices that are specifically designed for this purpose. These devices, such as current-limiting fuses, are capable of interrupting high-fault currents quickly and effectively, minimizing the potential for damage. In conclusion, correctly identifying the number of current-carrying conductors in a multiconductor cable is essential for ensuring the safe and reliable operation of electrical systems. The NEC provides specific requirements for adjusting the ampacity of conductors based on the number of current carrying conductors, and these requirements must be followed to prevent overheating and insulation damage. By understanding these requirements and applying them correctly, electrical professionals can minimize the risk of electrical hazards and ensure that electrical systems are properly protected. Always consult the latest edition of the National Electrical Code and consult with a qualified electrical engineer or inspector for specific applications and interpretations. Remember to use appropriately sized conductors and overcurrent protection devices for all electrical circuits. This will help to prevent electrical hazards and ensure the safety of people and property. Remember to consider all applicable factors such as ambient temperature, conductor bundling, and the presence of other heat-generating equipment when sizing conductors. These factors can affect the ampacity of conductors and must be taken into account to ensure that the conductors are properly protected.